everyone, in this video I will deal with Norton's theorem. So we have already studied about the Thevenin's theorem. We have seen how to find out the Thevenin's resistance, how to find out the Thevenin's voltage and how to replace a circuit with the Thevenin's circuit. So that was very simple, right? How to find VTH, RTH and all. So the Norton's resistance is also something like it is equal to RTH, means the procedure of finding the Norton's resistance is same as finding the Thevenin's resistance. So let us see what is this Norton's theorem. What does it state? So it states that any linear bilateral network, it can be replaced by the single equivalent circuit that consists of a current source and a parallel resistance, where the current is nothing but it is the current that is flowing through the shorted terminals and the resistance is nothing but it is the Norton's resistance, making all the independent sources equal to 0. That means voltage source it will be made shorted, current source it will be made open to find the Norton's resistance. That is when it is involving only independent sources. Okay, so any linear bilateral network, you have to remember these keywords because it cannot be applied to a non-linear network, okay, or unilateral network. So it is in any linear bilateral network can be replaced by an equivalent circuit consisting current source and a parallel resistance and a parallel resistance. Okay, so this is Norton's theorem. So how will your simplified circuit looks? It will be looking like a current source in parallel with a resistance. Okay, so this is A and B. This is the terminal A and B. We know Thevenin's equivalent, it was looking something like this, VTH, and here it is RTH, and this was the terminals A and B. Okay, remember that the Thevenin's circuit, okay, that can be converted to Norton circuit, and the Norton circuit can be converted to Thevenin circuit. Okay, anything is possible. How? See, if I want to convert this Thevenin circuit to the Norton circuit, what I will do? I will replace it with a current source whose value is V divided by R. That means VTH divided by RTH. Here the resistance is in series, but remember here with current source the resistance will be in parallel. Okay, this is RTH, nothing but it is equal to RN. Okay, this is something like this. But if you want to convert the Norton circuit to the Thevenin circuit, in this case you have to replace it with a voltage source whose value is I into R. That means this was IN, so it is IN into RN, and it will be RN which is equal to RTH. The resistance which was in parallel with the current source will be now in series with the voltage source. Okay, so this is the marked terminals A and B. This is how the conversion takes place. Okay, so next, why do we go for this Norton's theorem or the Thevenin's theorem? So remember, it is just for the simplification purpose. Okay, that means imagine you have a very complex circuit. Complex circuit is the uninteresting part of that circuit. Okay, what you want to do is you have a complex circuit inside this box and you have connected a load resistor and you have to find the voltage across this, current through this and the power which is delivered to the load. Okay, voltage across this, current through the load and the power delivered to the load. But remember, this is a very complex circuit. Okay, so now what we will do is using this Thevenin's theorem or Norton's theorem, we will find the equivalent, okay, equivalent of this complex circuit part of the complex circuit which is uninteresting one. Okay, so what we will do, we are going to simplify this and we are just having now a Thevenin's voltage in series with RTH, or this can be replaced by the current source in parallel with the resistance, and here we will be having RL. So how much simple is this, right? So now what we did, we took a complex circuit, we converted this to simple circuits. Now using this, we can easily find out the voltage across this load resistor using voltage divider rule. We can easily find out the current through this divider, that is using the formula I is equal to V by R. So here we can find out the current using the current divider rule. We can find out the voltage also. We can also find the power. Okay, so what happened? Our calculations now it will be rapid calculations. Our speed will increase using the simple equivalent circuit. So no matter, now if I want to find it out for 5 ohms, so after 5 minutes what if I tell no I don't want 5 ohm load but I want 10 ohm load. If you have a complex circuit, what you have to do, you have to perform all the methods once again if I change the value of the load resistance. But here what happens, if I change the value of the load resistance, again only with using the 2 or 3 steps what happens, I will be getting all the values, voltage, current or the power. Okay, so that is why we go for this Thevenin's theorem or the Norton's theorem. And the procedure of finding the Norton's resistance, it will remain same as in case of the Thevenin's theorem. Okay, so we will be having 3 different cases. One is only independent sources. Next one is dependent plus independent sources. And the third one is the only dependent sources. So remember how to find out the Norton's current. To find out the Norton current, what we will do is through which, okay, see if you have the terminals A and B, you have to short this. You have to short the terminals. You have to find out this current. This is nothing but the Norton's current or the short circuit current. Okay, Norton's current or the short circuit current. So just short the terminals. Okay, to find the Norton's current. In case of Thevenin's voltage, what we did, we were opening the terminals and we were finding the open circuit voltage. But in case of Norton's theorem, we have to short the terminals and find the short circuited current. Remember, we can also use another method to find the resistance in this second case, dependent and independent source. That is, first we can find out VTH or VOC. And we have to find out the Norton's current or the short circuited current, and then R equivalent or the R Thevenin or Rn, that will be equal to VTH divided by IN. Okay, so this will be giving you the resistance. Okay, that is in case of dependent or independent. Or the second method is to, okay, if you have this terminals A and B, you can connect a voltage source VDC. Okay, then you can pass this current IDC like this. So if you take the ratio of VDC and IDC, okay, and remember using this formula, you have to make the sources equal to 0. Independent sources should be equal to 0. Okay, so that is using this method. Then you have to find VDC divided by IDC. So that will give you the resistance. In case of dependent sources only, if you have the terminals A and B, you can use 1 ampere test source, okay, or you can use 1 volt test source. 1 volt test source. This is in this case, third case. 1 ampere test source or the 1 volt test source, and you have to again find out the voltage across this. Okay, voltage here, the current through this, you have to find it out. Then you will be getting the resistance using the ratio, that is V divided by I. Okay, you will be getting the resistance. Remember, in case of dependent sources only, our VTH will be equal to 0 and our current IN, that is equal to 0. Remember this. Okay, this is an important point, that is in case of the dependent sources, because it will be inactive, right? Dependent sources will be inactive without any independent source. Okay, so VTH or IN, that will be equal to 0. So this is all